Let's see. I gotcha. Let's see. Hopefully I got enough space. I got like 200 gigs. Let's see.
Yeah, I have space too in case you want to switch.
Hopefully it doesn't conk out halfway. Okay, we're good.
Okay. So, paper number 12. Remote epitaxy. So, once again, epitaxy. Using graphene. The best material ever.
This paper actually.
Enables, not really, enables growth of stress-free gallium nitride. So, this is going to play, okay, good. I highly recommend this YouTube video by Veritasium that we were watching when you all came in.
Oh, that's a recent one.
Yes, about blue LED, which is using gallium nitride and MOCVD synthesis, and they have a very good band structure review, and not super important for this paper, but you know, overall, and very helpful animations about the MOCVD process and like the effects of having some sort of underlying substrate layer. It's not the exact same thing, but if you want good animations and a little bit of history, very good video. I recommend. So in this paper, they use metal organic vapor phase epitaxy, specifically MOCVD, I believe. So this process is different from NDE, as in they have this carrier gas. So they've dissolved the element in question, the gallium, and into some sort of precursor. They evaporate it off and send it in as a gas. And you, once again, I think they have the substrate heating. They don't talk about that as much, but they really talk about the different types of gases they use to flow these. So there's a chemical reaction happening in order to form the crystal, as opposed to just physically throwing your atoms at the substrate and it sticking. So there's usually like some trimethyl something, or I forget all the different reactions that occur, and they're not super important. Just knowing the mechanism that there is a chemical reaction happening in order to make these crystals is what you need to know. And they do talk about the effect of different like pre-treatments, I believe, like flowing different gases over the substrate. So just make a distinction between those as well. But they describe that pretty well on paper. So yeah, metal organic CVD. So you have some sort of metals bonded to an organic compound as your reaction. So much higher pressure than MBE.
Is that it uses higher pressure than MV?
Because yes, it's around like just ambient pressure, really, like 10 to 760 torr, and just because you have all these gases flowing. So the mechanism that this is happening has nothing to do with it's at a lower pressure or anything. It's that the chemical reaction is happening.
So when you're trying to deposit, you dissolve first, and then in that state you it's evaporated, is what you're saying?
Yeah.
And then it reacts with gases that are already in the chamber to kind of like aid that deposition onto the surface.
Yeah.
So then what kind of gases are we looking at?
In this case, nitrogen for gallium nitride.
Okay.
I think they talk about some other ones that they flow over the substrate. It kind of depends on what you're depositing. And direction, as we learned in the Veritasium video, the direction of the gas matters too.
Yeah. Needs to be laminar, right?
Yeah,
The flow.
you want a laminar flow. You want it to be able to be hitting the substrate. Because normally it just flows over the top of it, as opposed to molecular green epitaxy where you're directly at the substrate, but this is gas flowing on top of it.
So the gas is also kind of like a material precursor to the film that you're making. Can you have like oxygen then, or does it always have to be?
I think in things like ALD, they'll spray like water and stuff in there.
Oh, okay.
So you can have oxygen, but this is where it can get contaminated and cause defects, which aren't great. but sometimes if your process is good enough and clean enough and your reactions are what you want them to be and everything's going in the right direction, you can get good crystal quality. And it's cheap. So it's more used than MBE for sure, even if you don't have this great of crystal quality. So, yeah, I think CBD is probably the most used physical vapor deposition method.
In California.
True. Yeah. Whatever. Deposition. Thin film deposition.
Probably.
Let's see. So, paper itself. The problem was there was strained and dislocated gallium nitride. Also in the Veritasium video. They used to grow it on sapphire a lot, and that doesn't have the same lattice constants in plane as gallium nitride would be. So this is not a 2D material. Gallium nitride is not a 2D material, unlike WSE2. So it will covalently bond to the substrate. And yeah, it has a nice band gap, so you want to use it.
Okay.
But it will get strained or stressed, like I had in the picture in the other presentation. So yeah, it'll just, that bottom layer will move in different ways and cause different stress and strain, which they measure a lot with XRD, so your peaks will shift. And you're kind of stuck that way. So what did they try to do? They went, oh, there's this van der Waals epitaxy thing. They don't have stress or strain because there's no covalent bonds. So let's try and use some sort of intermediate thing, because we still want to orient our crystal growth. We still want to have the effect of the substrate. So let's do this intermediate thing called remote epitaxy.
They use graphene for that.
So you can do it. They use graphene. You can use other types of 2D materials, but the main thing is that there is a thin layer of a 2D material in between your gallium, your gallium nitride and your substrate. So,
Okay. So they are saying because of graphene it's too thin, right? I mean, it's a 2D material. So, like, I don't know, like the interaction with the substrate are still there, so they can grow the, okay, they can grow the crystal.
And yeah, you can kind of see there's still this charge transfer from the substrate.
Okay, yeah.
And the 2D material can also help with that, you know, conductive,
Yeah.
if you wanted to. So that
Yeah, and also the
would affect
orbital
your
peak.
choice of 2D material. Excuse me. So you can have some sort of polar substrate, and it's going to affect what grows above it, regardless of your 2D layer is thin enough, it can still have an effect.
And that charge transfer was like the polarization thing in that. Okay, cool.
The polarity. Yeah. So yeah, you can see we have this kind of thin layer there.
Wait, one more time. Why did they use graphene for the 2D material? For better growth?
Graphene is just easy to get very clean. So
Okay.
I think that's why they mainly use that in this paper.
Were they trying to combat the lattice mismatch?
Yes.
Okay.
That is the whole reason why you use this 2D
2D
van der
material.
Waals.
Okay.
Yeah, it's the van der Waals bonds.
There are some points in the paper that like kind of question the cleanliness of the graphene though. So I don't know. Wait, is this like later on in your presentation or something?
I can just talk about it.
Sure.
So, are you referring to like exfoliated graphene versus just like what they see, or just generally?
Okay.
Just like what they saw.
That's a
I don't
good
know.
question. That's a good question. So like, what process did they
to
use
make
to
it-
process the graphene?
Yeah,
Like
because,
that,
yeah.
Yeah.
Because if
so,
they are doing like exfoliation,
exfoliation,
and which kind of exfoliation?
Mechanical
good old
exfoliation.
Scotch tape.
Yeah, that's good.
It's not
That's
taking a
what-
tape in and do these. I
Yeah,
don't think so.
I did that in
Many times.
undergrad. They still do that, but that's more physicsy side, not so engineering side.
Yeah.
But this is silicon carbide, is their substrate. So they take silicon carbide, it's got carbon on the top, they heat it up, and it makes really good epigraphene. epitaxial quality graphene.
Okay.
So it comes from the silicon carbide?
Yeah, because
Oh.
there's carbon on top. And they heat it up, and it makes that graphene layer.
That's
It's
what
really
I
nice.
was super wondering. I was like, wait, the thing actually comes from
Yeah.
the silicon carbide? I was like
Because
super
they say
confused.
silicon carbide, but you gotta remember there's that layer of graphene on top of it, and it acts like a layer of graphene that you put on top of there.
So wait,
But they're using the silicon carbide for the polarity, the charge.
Yeah, so there's still
Stuff.
silicon underneath
Yeah,
it,
yeah.
and then you got this layer of graphene.
So the graphene still allows for that, like.
Yes,
Okay.
because it's thin.
Because it's thin, yeah, thin enough
So
to
they
allow
grew-
that.
I
they
see,
grew
I
the
see, I see.
graphene from the silicon
Yes.
carbide. They didn't just put it on there. It just
And
comes
also
from
due to the
from-
electronic
and
properties of
they
the
grew it
graphene.
by heating
Yeah.
it, you said.
Yes, you heat it really hot, and it
React.
arranges it enough that
The
it's
electron
graphene.
properties of the silicon,
What?
underlying silicon, because you want the polarity from the silicon substrate.
Yeah, but I mean the
So-
electronic properties of the graphene allows,
Yeah.
you know,
It's
the electronic,
Yeah.
because it's conductive. And because of the p orbital. So if it is
Mhm.
conductive, you can just have the electronic property of the substrate over the other one, right?
Yeah.
I think
I
so.
don't know if they mention that the properties of graphene as much. I think they're more so saying the substrate is affecting it. But I'm sure that probably is something too. But,
That's so
it's called screening. If you want to look at it.
Screen, yeah.
Screening.
Like, yeah,
Try to
graphene is
screen.
not good. Is not good to screen the other one.
Mhm.
That's why it
Yeah.
works, and right?
Yeah.
So then the silicon, I'm still on that, it grows from the silicon carbide.
Mhm.
So does the topography of the silicon carbide make a huge difference? Would you want to like really smooth it? Oh,
Mhm.
okay, I
Mhm.
see.
So you're only exposing like a carbon layer to the top. You
Mhm.
heat it up and forms graphene.
How do you expose just a carbon layer though?
You cut it really, really carefully. Polish it in some certain way. There's
Really?
ways you can do that, I think.
What was it again?
You can polish it really well. I'm not quite sure. Or you can grow it in a certain orientation and then that just happens to be its top layer. It's like having C-plate sapphire or something. They just mill it a certain way. So that one certain plane is exposed. And they've gotten really good at it.
That's
Like, I
really.
think that's one of the more common ways. So, yeah, the 6H silicon carbide is the crystal orientation that it's grown in, the 6H. So,
This push the crystals around with the AFM tip. Is that the
Yeah.
graphene?
that was good.
That's crazy.
I know, that was amazing.
Well, it's not, what do you mean, is that the graphene?
Dude, I
Meaning,
don't know how to
like,
do that.
Pushing the crystal. I'm assuming the crystals of the graphene are being pushed around.
No,
It's
No, the
the
crystals of the
gallium
gallium
nitride.
nitride, yeah.
Mhm,
Yeah.
So that's the
Oh.
gallium nitride that is just grown on top of it, and they're doing that to show that it's not bonded to anything really. It's only van der Waals bonds, and they can just push it around. with
Oh,
an
I
AFM
see. I
tip.
see.
How do they polish it? So that's.
Huh.
Isn't it only like one atom thick? How do they polish it so that it
I
doesn't like?
think heating up helps too, get all the gunk off of it. There's certain surface treatments they use, I think.
Okay.
I'm not super familiar with that because I just get, nice polished things that I order off the magic. Yeah, it is magic to me. So yeah, if that'd be something to look up.
Can you
probably
say
ask
again? How
us
they
about
show?
that.
How they show? This is Van der Waals, like where the graphene. How you know? How you know?
Oh, because
there is no
there's
point.
literally no atoms there. There's a blank gap of empty space.
Okay.
They're not close enough to bond
Okay.
in a covalent.
The buffer layer. That's,
I don't know what the buffer layer is necessarily. I was gonna look that up again.
Okay. Yeah. So. Okay.
Oh, so it's not like substrate and then directly on the substrate is graphene and then directly on the
That's
graphene
what I
is gallium
thought it
nitride.
was.
But how is
That's kind of what it is.
But
How
what's
is
the,
that
how does the
though?
van der Waal come in? Because isn't that like empty
after
space?
graphene? So graphene is too
So there is a
pure.
gap.
Okay.
So it's
Yeah,
not
there
like
is-
three contact points.
You
or
can
two
look
contact
there,
points.
it's less than 2
Yeah.
nanometers.
Yeah.
That's a small gap. I
Which
mean,
Which
it's
is
similar to the distance between on the HAA and DF. That's similar to the distance between the actual atoms.
If
Yeah.
it's grown from the silicon carbide,
It's like
How is it-
3.7 angstroms.
how is it
It's
not
nothing.
covalently bonded
Correct?
to
Yeah.
the bulk of the silicon carbide, that graphene layer?
That's
It's
amazing.
Just van der Waals bonds. That's what happened when you heated it up and grew your graphene on top. Is it disconnected?
So the graphene grows from that covalently bonded carbon like plane that you're.
However, I forget
Okay.
the silicon carbide.
I
was
didn't
like-
know with
Okay.
AFM we can see like this, blank space without any
Yeah.
bonds. I was
Yeah,
thinking
cool.
to be sure of that,
AFM
you need to
can get
do
like you can get nano because that's my work is like using PFM I use but like it's the same concept with AFM and my recent research was like nanoscale work.
Yeah.
You can get
Yeah.
you can get like really small.
Yeah, so these are TEM So they've done a cross-sectional cut. It's a very tedious process.
For sure.
And yeah, you have to get everything aligned really well. So you're taking, and it destroys your device usually.
Yeah. But AFM is contact specific, like you have to
And
make
that's-
contact with the material, and that's the issue, is like a lot of,
Well,
especially with the
yeah.
perovskites, is like a lot of the surface of the material is affected by is like very sensitive to the surface, and especially the materials, when you apply too much force, where you have like contact on the surface, the mechanical properties of the material are affected.
Yeah, for sure.
Which is why AFM is like only really relevant for like
Yeah,
certain
so I'm
class
just
of
looking at these labels on the leftmost image, right? So it shows we have like 6H silicon carbide, we have graphene, SiC and then the gallium nitride. Is that how the structure is?
Yeah. So I don't know why they were referred to buffer layer as like something different. I think it's just the empty space.
Empty space.
The empty
in between
space.
the
Yeah.
graphene,
the like van der Waal.
like gap.
Okay.
Yeah, the
Is
gap.
that like sandwiched between the graphene, or in only one, like the
It
one
would be
side?
above the graphene and below the graphene.
Yeah.
Okay,
both.
so
The
there's
graphene is in
something-
the middle.
Yeah,
Yeah.
yeah, yeah, sandwich.
It's
Which
just
buffer
jam.
layer can mean other things too. So that's why I was confused by that. It can mean like a full other layer of some
Yeah,
type of
yeah.
material.
everybody knows.
Which, yeah, I don't think that would.
But I assume they did like plot like XRD or TM plots to like figure out, and they didn't get any like. I didn't read the paper, so I'm like, this is me.
Yeah.
Maybe or like I could have read it, but I assume like they would have gotten a material peak that they knew was that buffer layer, but since they didn't, they just called it buffer layer.
They did XRD.
XRD,
Yeah.
okay.
To find, and they found a
To find gallium nitride.
To confirm
silicon
like
carbide,
the
graphene.
structure. Okay.
Okay. XRD.
Oh.
yeah. Well, they did glancing angle
Yeah.
XRD.
Grazing
Yeah.
and
They
stress,
should
which
do
is just a finer.
Yeah.
XPS, you know?
XPS
It's
isn't
the
gonna work
grazing
right here.
incidence.
No, why?
Yeah, XPS, because it's
Why?
surface sensitive. So
You
you
see
only get the
the-
top
Oh, yeah.
gallium
Yeah.
nitride layer.
Just the top, okay.
Yeah, you wouldn't be able to see the graphene, it'd blast right through it.
Yeah, XPS is like
That's a question.
yeah.
That's an important question.
you don't
yeah.
get a lot of the bulk of your material on XRD.
Yeah, yeah.
XRD you do.
Yeah.
I think XAS and XCS are the other two. I don't know. I told myself to look over the scattering notes because I was like, I was reading one of the papers and I was like, oh, I gotta look
Yeah.
at scattering notes.
I know.
Yeah, because I know with SPS you can know exactly, you know, the orbital was interacting and you can know if there is a like
Chemical bonding.
chemical bond. Yeah.
Yeah.
So
Mhm.
if there is a chemical bond between them, but if it is on the bulk, yeah, we
For
cannot use
later
back.
things, it's not as great. If
Yeah.
you're trying to figure out what kind of compound do I have, XPS is great.
Yeah, it's great. Yeah. Really nice.
So yeah, remote epitaxy made unstrained gallium nitride crystals, said that they weren't really bonded with the substrate enough to be able to push them around with an AFM, which is cool. And they were able to still have the effect of the substrate so that they stayed oriented how you wanted them to be. I'm not sure why they didn't grow like a full coalesced film, but they were able to show that the like grains were large.
I think they said that this was like the first step into growing full coalesced film, so I
Yeah,
don't
I
think they
think so.
knew how to do it.
Which this paper comes out about a year after like this whole remote epitaxy became like big and popular. Like there's a big Nature paper about it and stuff. So I'm not sure why they didn't go in depth more. But maybe it's just kind of one of those, oh, we're gonna explore this one little thing a little bit better than other papers did or something. Or yeah, they didn't want to choose a paper that was too in-depth about this. Let's see. So we think this one was probably chosen by Garton,
Oh, okay.
according to Bonnie.
Really?
Probably. I do a lot of epitaxy stuff.
Yeah.
I thought her work was more in ferroelectrics.
She does both.
I didn't realize the epitaxy part of her work, I guess.
Dynamics, structure,
This can be used
strain
with
effects. The
electric
lattice,
systems.
okay, that's something that we need to read. Measuring strain, okay.
But yeah, so it's kind of the same things, kinetics and thermodynamics again. But there's a lot more emphasis on like strain and stress from XRD. So I could imagine Yeah,
Did they metric strain at all?
XRD, I think.
Using
They
XRD
don't-
to measure strain and stuff.
Yeah, they did, and then they had
Interesting.
plots. Yeah.
Which
Oh,
plot?
see.
Wait, no, they didn't have plots. No. Give us some.
Well, there was the
Yeah,
Yay.
there's the arrows up and down.
Now we're not at a time crunch.
Wait, so are
for
they
lunch.
able
Figure
to
one, C.
um,
oh, okay.
determine
I
the
got you.
strain or like characterize the strain
Mhm.
through XRD plots?
Yes.
And is it that like shift and peak, or is it like
Shift
the?
and peak.
Oh.
I
I
believe
was
so.
expecting a strange stress
Yeah,
plot.
it's the.
Like,
not
me,
that
what do you
kind.
mean?
Uh-huh. Thankfully, not that kind.
What-
It is the 002 peak position.
I got you.
So they call.
I thought shift and peaks were okay. This is where I need to review
I thought that
XRD because I'm like, what the fuck?
There's compressive intensal.
because
Yeah.
The peaks can shift.
I heard that like strain causes peaks to broaden. I don't know about
That's what I
necessarily
was
I
thinking
think
instead
so.
of shift and peak. I thought it was a broadening slash.
Okay, it does both.
But I
They also have full width
didn't
max
know.
in there too.
That was
remember that-
mentioned in the first
That's more
paper
about-
too.
Yeah, I remember one of the papers had that. Yeah.
And I made a note like
Know how to do
review
this stuff.
because I also heard from the girl in my lab is that she thought it was Garmestani's paper. She doesn't remember me. It's 2 years. I don't blame her. Where she was like, she read a paper and it showed you like an XRD plot, and then in the question he gave you like a new XRD plot. He was basically like asked you a question like, okay, now that you know in theory how to read this XRD plot, like tell me what this XRD plot is telling you, which
That's it.
makes sense. Which is like the normalization stuff we did we took the three of us took scattering class, and it was like being able to like normalize the points and then like read a XRD plot and tell you like, okay, which peaks align with which.
Was that one of the
Plain
super
material.
alloy? Was that one of the high entropy alloys?
feels like a
ones?
lot.
Yeah, that was the high entropy alloy
Yeah.
with the circles.
Either the
Yes.
plot, either the color thingies. Yeah, the one that
Yeah.
you just showed.
Two,
Yeah.
the two.
No,
I
not the
think
one that you
both.
just showed. No, it wasn't that one. It was
Both
the
high
pole
entropy
figures. The
alloy.
pole figures. That's what it's called.
Yes.
Yeah.
Yeah,
People
both.
will probably do that. This one, you're not actually seeing any XRD like.
No, they just kind of say it happened and here's
Yeah.
what it.
So this one, I feel like it'd be kind of mean to be like draw the XRD.
Yeah.
Yeah, we
don't
That's
have
what
anything
But I
it
say,
else.
yeah, I think
Yeah.
the
why it's certain.
paper
That's
one
what
was
this
like
is.
I think it was like one of the I don't remember which. I think incident beam XRD, and then I could see him being like, hey, a very basic level of like, this is an XRD plot. Like, tell me why we're using this specific mode of XRD, or like, okay, now you're given this XRD plot.
I
Like,
will not
what,
be doing
what
that.
material?
Which-
Not happy.
But yeah, but the other
It's probably the first paper.
those other papers, the high entropy
Yeah.
alloys, there's 3 of them, I think.
Yeah.
Something like that. I read 2 of them, and I think they all had the like pole figures, and one of them also had stereographic projections, which I think a group met yesterday and talked about it. And I was like, well, I hope we meet again, because I don't know. I feel like there's a general understanding like people are trying to get through papers this week, and then people are trying to meet, and I was like,
Mm.
I mean, I'd love to, but I can't. Like, we got to do this next week. So
Yeah.
But yeah, but one guy apparently I saw like I was skimming the notes that they had taken because they sent them in the Slack after, and one guy apparently was like really good at stereographic projections, which I was like, that's crazy because we learned it in class, and I was like, that I tried so hard to learn it. I was like, this doesn't make any fucking sense to me. Like, this is so hard. But yeah, apparently one guy was really good at those. So
I think we met yesterday and had some lattice strain to the peak width kind of stuff.
Mm-hmm.
Like some people had taken a class and learned about that and all about that peak fitting.
yeah, that's probably the scattering theory class.
Yeah.
Because I remember doing that.
There's this one
I
dude.
just can't recall it now.
I wrote down their names and stuff, but they're super good at it. I think I have some notes from that class that I could share with you. Or not that class, not the class, but
I took
the
the
actual
class,
like
so.
go over yesterday.
Yeah, I saw they posted notes in
Oh,
the
cool.
Slack.